go over like what Stokes and Green's theorem is doing in like a geometric sense? There's like should draw a picture.
Yeah. No, this is helpful because a lot of them, I use the gradient theorem a lot in these. I was noticing just and so that's one of them. So, you know, we have the fundamental theorem of calculus. And then the gradient theorem looks an awful lot like that. Gradient of f dl b f. But there's a geometric difference between this one and this one. Because this one is like, it's just a 1D function. This is a total derivative. This, it's like a topographic map, remember we had last time, and then this is a particular trajectory along that map. So if we're drawing the contours of f from above, so if this is f and f is big here, f is little here, which way does the gradient point on those contours? Towards higher values, right? Perpendicular to the contours towards higher values. We went through that last time. So I would put A and B in there, but let's put B here and A out here. So how do I interpret that gradient of f dot dl? So I want to go from A to B somehow. That's one way I could go. I could also pick a straight line. I could go this way if I wanted to. And along this trajectory are the little vector elements dl. Or along this trajectory are little infinitesimal vector elements dl. Along this trajectory are infinitesimal vector elements dl. So does the answer depend on which path I take? No. So that's what's really kind of shocking about this. Why the gradient theorem is really important and powerful is because it tells you that this particular integral is independent of which path you choose. You choose any path I want to go from A to B, and I get FB minus FA. Does that make sense? And so, what if I go in a closed loop instead? Closed loop back to where I started. What's the integral of that? 0, because it'll be f of a minus f of a. So that's another frequent one that I like to put on midterm, because once you've seen that that's what it is, that's what it is. A closed loop of a gradient, of the integral of a gradient along a line is 0. So there are a whole lot of ones that I put in about gravitational potential energy, which is a good example. The force of gravity is the gradient of the potential energy. And so a lot of the questions in the midterm touch on that kind of relationship. And so I'm using this thing over and over again and talking about, like, can you go uphill to school both ways was the one for the homework. But I have a kind of similar one about riding my bike, and one of them I have another one. I don't remember what the premise of the other one was. But anyway. Okay, so that's this one. So what about, what's my next one? What are the two other calculus theorems? Stokes. So Stokes tells me what? That the curl of a vector field has something to do with the vector itself. What else do I need to fill in? Dot n is an area integral here, and the area is a closed area or not. So 2, 3 over here, right? here. So what is it on this side? Kind of terrible erase. Made it less erased. So this is a .dl one as well. And this one, is it a closed loop or is it an open loop? This one's closed. So this one, the thing to keep in mind is imagine the loop. So there's a closed loop on the right-hand side. And now we're talking about integrating around in a circle. And it's a vector field that's embedded, whatever, doing its thing, whichever way it's going. And you're thinking about the curl of that vector field puncturing a surface that is enclosed by that loop. So maybe I can just, let's just say this is the curl of the vector field, not the, because it's easier for me to draw it. So that would mean that the vector field was like going around like this. Is that right? No, other way. How did I just use the right hand rule there? I want to wrap my fingers around the direction of flow, and then my thumb is going to point in the direction of the curl. So this way, kind of zooming around the loop like that. So if I integrate around here, I'm going to get some positive. If I integrate over that area, the curl, I'm going to have some positive normal direction curl poking out. And if I integrate around the loop, I'm going to add up as these vectors are kind of aligned with the loop.
Where are you getting the direction from?
So, oh, the direction of integration or the direction of the flow field? The V.
The direction of flow.
Yeah. So these guys are V's, and this is the curl of V. Sorry, I should probably have used it. Make that I did a right-hand rule, so I put my fingers in the direction of the swirly motion, and then my thumb is pointing in the direction of the curl. And so you can see now that actually, so this there is one very subtle point about what this means, which you can use the right-hand rule to figure out. Did I draw DL in the right direction or not? Is V.dl going to be a positive number or a negative number? The way I drew it. Negative. But the integral of this, with the normal being this way, is going to be a positive number. So I have a sign problem. And basically, it's very hard to figure out. You could probably figure out a right-hand rule where you were like, I want the normal to be in the direction, like wrap my fingers around the DL direction, and then I want my normal to be in this direction, which would have worked for this one. I didn't do it that way, but if I had done it, it would have worked. Does that make sense to everybody? So, but aside from that, this is the geometry that you're thinking of. It's an area bounded by a closed curve, and you think about the curl vectors puncturing that area in the normal direction. What if I drew a different surface, different area, that was also enclosed by that same curve? Does that change the Stokes theorem? It doesn't, right? So as long as the area of this integral is enclosed by this closed circuit, this holds true. So I could take a flat one, I can take one that bows out, I can take one that bows in, and the amazing geometry of this dot plus the magic of the curl makes them all the same. So just like this one, the gradient was special. This would not have worked and been path independent unless this thing was a gradient. This would not work for arbitrary areas enclosed by the same curve unless this thing is a pure curl. Okay? It's kind of the same concept, but in two different geometries. And so what we have hinted at the Helmholtz decomposition just a little, which is to write a vector field as a combination of a gradient and a curl. One of the midterm products kind of walks you through that, the seismic wave one, which we can do. It turns out that you can do that all the time in kind of a very generic way, and we're going to use it a little bit when we think about PDEs later. So you could write, so any vector field can be written as the gradient of something plus the cross product of something else, plus the curl of something else plus a constant. So that's the Helmholtz decomposition. Helmholtz. Okay. The last one is what? The divergence theorem, yeah. So the divergence theorem, what have I got? What kind of integrals have I got? I got a divergence. And there's some kind of integral. And equals some other kind of integral. So how do I fill in the pieces?
The left-hand side is the volume integral.
This is the volume integral. And then the right-hand side is an area integral enclosing that volume. So it's a closed area. And this is another when I was in grade school, if you got punished, one of the things you had to do was go out into the playground and knock the chalk off with the erasers. And that was like major, it was terrible work. Got like totally dusty. Anyway, okay, is this a scalar or is this a scalar or is it a triple integral because it's a volume integral? Is this a scalar or vector on this side? Scalar. So what does this have to be? Scalar. So how do I make it a scalar? Start with a vector, like the normal vector. So there are two, the normal is appearing here and here. The lengthened piece is appearing here and here. All three relationships are scalar relationships. Right? So there's some symmetries about this, which makes it a little simpler to think about it when you're thinking about how to build it. Well, I will say, you're welcome to use the notes on the midterm, your own notes and the notes from whatever. But don't use the internet. So, don't use Wolfram Alpha to do an integral. That's where we'll draw the line. Okay.
Wait, so you mean like in the midterm we can?
You can use your notes if you want to look back and refer to something. It's an open book. It's just not open internet. So. Yes, which is, and I mean, and it actually is kind of open internet in the sense, but it just like. That we could draw the line there, that makes it simpler, because then what I'm hoping, a lot of the questions are, I'm looking for you to find something that's like in the equation, and if you just plug it into Wolfram Alpha, it'll just tell you the answer is 0 without knowing why. That's not actually the target. The target is that you would see why by looking at how it's built. So that part should be there. Does that make sense? Okay, so those are the so what's the geometry on this one? So I have a volume. What's inside my volume? Vectors. And if they're all emanating from a point, then they're doing what? Diverging. So if I put a volume on those, how do the arrows piercing in the normal direction relate? That's what this says. It says the divergence inside the volume, which is a scalar field, and here it would be positive kind of everywhere because the vectors are going out, integrated over the volume is going to equal the vector dotted into the normal direction. So how many arrows of the vector are pointing out integrated over the surface? And the other example we thought of was, what if all these arrows are converging next door into a region of a volume of negative divergence? If we drew a bigger area to include both, and the positives integrated up to the negatives, what can we say about the vectors coming and going? It'd be 0. And we could get that a couple ways. We could get it by having them all going out over here and all going in over here. Or, interestingly, you could make it 0 because they could go out here and never go through and just go into the neighbor. Like, they might not ever pierce the surface. That would be allowed. Maybe instead of they diverge, but rather than going through, they come over here and poke back in over there. Does that make sense? Those two scenarios are both covered within this divergence theorem. So the fact that there are arrows poking through does not mean you have a net divergence. You have to integrate them up and sum them up. Yeah?
When you say net arrows poking through, that's like poking through the surface of the volume?
Yeah, I'm thinking of this V dot n hat. So it's poking through the area enclosing the volume is what this one means in this case. In this case, the curl dot dn means the same thing, but it's not a closed surface. It's an open surface that's enclosed by a line, which is the integral here. Make sense, everybody?
Was the condition that for all of these theorems that the vector field is conservative? Or?
Good question. This, a conservative, so in this, if we think of this as a force rather than, this would be the conservative forces, would be this part. This would be the non-conservative forces. And that's because if I apply the gradient theorem to this, I find out, hey, look, there's an underlying function. Here we're calling it phi, here we're calling it f. It's just a function of space. And I can figure out my integral of my gradient along any path just by evaluating that underlying function. So that's what we mean by conservative. There is a potential field, phi or f, that is underlying the forces everywhere in space. This one, though there is a vector potential underlying it, this psi, it is not path independent. If I try and do this part, I will get an answer that depends on my path, which path I choose. And if you stare at this long enough, you'll see that this one is actually the one that's telling you about that. This, if I do a closed loop, so let's do that. So if I do any loop A to B, I get a result like this from the conservative part. And if I go back to a closed loop, what do I get? 0. But this one is telling me, hey, if I do a closed loop and there's some curl in it, I don't get 0. I get whatever that integral is. So this is not necessarily 0. Right? Does everybody see that? The amount of curl in this area tells me how much my non-conservative force is going to add up when I go around that closed loop. So the bicycle problem in the midterm is doing exactly that. First I say, let's do a closed loop. Let's go 2 paths to get from point A to point B. And I say, is it possible for me to, or earn more potential energy going one way or the other? No, it's the same. Then I say, if I go back to where I started, do I gain any or lose any potential energy? No. But I had to exert energy riding my bike. Why? Because there were non-conservative forces, friction, and me applying the brakes that would have cost me some energy. I don't get the energy back. And actually walking versus bike riding is particularly where you experience that. When you're walking, you have a lot of energy that you're losing. Like you're just burning more calories walking the same distance, whereas on a bike or a roller coaster, even better, you can get back to where you started with very little extra energy input because it's nearly frictionless. That's how they build it, to make them so you gain all that energy back, almost. That make sense? Okay. All right. That was good. That was a lot of stuff. Oh, so I want to. So the secret triple products. This one is just not really a triple product. It's just a new name. This is the Laplacian. So the divergence of the gradient is the Laplacian. And if I write it down component by component, it looks just like, oops, not component by component, sum by sum. It doesn't have any cross terms. It just has the second derivatives piled up. Is that true if I do it the other way? If I take the divergence of a vector and then take the gradient of that? Tell me what the x component of this is. It'll be d by dx of d by dx of the x component of v plus d by dy of the y component of v plus d by dz of the z component. So these are not the same, and that means what about the operators? They don't commute. And in fact, this is a vector, this is not a vector. These definitely are not the same thing. Okay? So these are two of my rules. What about the divergence of the curl of a vector? Let's do one component. So how do I calculate the divergence? Take the what of the x component? X derivative of the x component. So let's just do that one first, d by dx. And how do I find the x component of the curl? I build this funny matrix, and I take its determinant, right? B sub x, B sub y, B sub z. And which, so, so this is the x, this is what I'm supposed to be getting the x component out of. So what's my x component out of the determinant there? It's got to have I hat in it. So what are the two patterns? You go down this diagonal, or I can jump and go down that diagonal, right? So that would be d by dx. Oh, it's only going to couple of that. Sorry. D by dx of d by dy b sub z minus d by dz b sub y. Is that obviously 0? No. But if I wrote down the d by dy part, I would have a d, let's see, dv by dx with a minus sign. And then plus dvx by dt. So this one and this one, oh sorry, this one and this one are the same, but with opposite sign. See this? Because ddx and ddy commute, and dy and dx commute, and they come out with a minus sign. What happens to these terms? I'm missing one part of my divergence, right? I've still got to take the ddz of the remaining part of this, and that will come and cancel these two out. So this is always 0. Okay? So a game that I will play a lot is to give you something like this that's a curl and ask you to evaluate that integral. How does that operation go? If v is a curl, and I ask you what that integral is, what do you do?
Say it's 0.
You move it over here, and then you say this is equal to the divergence of v, but the divergence of a curl is always 0. Does that make sense? So putting that result together with this fundamental theorem is the kind of thing you would frequently do. So what are the other triple products? We have that one. What about the curl? What else can I do? I can make the divergence of the gradient. I can make the curl of the gradient. What's that? Maybe we can see it if we just even write down the determinant part. D by x, d by y, z. Then I would have d by dx of phi, d phi y, d phi z. Okay, so what's the I component of this? D by dy of d by dz of phi minus d by dz of d by dy of phi. 0. The same thing. Every time it's going to give you the partner that has the opposite sign with the reversed derivative order. So this one is also 0. These are just 0 because of the pattern and the fact that the derivatives commute. So it's just like you figure out the pattern and then you switch the order of the derivatives and you get something plus minus itself. So there's no magic here, it's just built into the patterns of derivatives that are coming into these divergence and curl and gradient operators. Okay? It's almost like odd and even functions, in that it has just symmetries built into it. Because if you ask, the same way you could say, what's the odd Taylor series component of an even function? What is it? So what's the third power, the coefficient of the third power of cosine? 0, because there won't be any odd powers in the expansion of an even function. So this is kind of the same thing. It's sort of like odds and evens, like they're just canceling each other out when you put this together. Does that make sense to everybody? And there's a similar thing in matrices too, where you can, the product of a symmetric and an anti-symmetric matrix will give you 0. So there's lots of these kind of symmetries built into these kind of things. Okay? Are there any more triple derivatives that we've missed? Starting with a vector. If I have a vector, what derivatives can I take of it? Curl, the divergence. And the divergence is a scalar, so the only one I can do is take the gradient. The curl is a vector, so I can take its divergence, or I can take the curl again. So there is one more that's missing, which is this guy, and this is the one which I always, this is the one that's, I forget which way to do it. B, A, C. I think it's this. Gradient, divergence. I'm going to do this more fun. I'm making it wrong, but I'll write it down anyway. I think that's right. And I don't remember whether it's a minus sign or a plus sign. But something like this. This one is just an ugly one, which you can look up. Okay. Are there any other triple products that we missed? Or double derivatives, I guess I should call them. These are really not just triple products. I did both operations I can do to a vector, and I made a vector, and I did both operations I can do to it. And I made a scalar, and I did the one operation I can do to it, so that should be all of them. Okay? All right. So let's talk a little bit about maybe one of the. So what are the patterns in the midterm questions? How do they normally go? Did you recognize any systematic things? It's always a units question, and frequently the units question is this. Which one? The last one. Incroyable or unbelievable in French. This is a good example of what I like to do. This one, or the other one is the critique of your friend, where it's just like put down a bunch of things that can't be right and ask you to tell me why they're wrong. Right? So even without knowing anything about the underlying science, the math can tell you that these things have to be wrong. So that's a really important skill to build. There will almost certainly be a question like that, of some flavor. And that depends on units, so matching units both sides, matching dimensions both sides, matching vector scalar covariance both sides, matching size of matrix to size of matrix both sides. Those kind of things are all the same flavor of is this possible or not. So if you take a look at those, you'll see how you can run through and check through those quickly. Does that make sense to everybody? What are some other patterns? Using this one with gravity frequently comes up. Maybe there'll be another one like that or something similar. What about, these guys almost always come up. Both of those two. So those 0 ones, which is normally to simplify a problem that starts off in some complicated mess like this, and then one of them is 0, and then the remaining problem is actually simple. What else? a Taylor series and Fourier series. There will certainly be a question about either or both. Yeah.
We have time to go over the Taylor series question on 2014,
Yeah.
especially the last, like, 3
Yes. All right, this is actually this is a weird one. I've never seen anybody write this down before, and then I was like very pleased to think about it this way. Thought it was a nice example. So the basic premise is, if I have a function, I could write it both as a Taylor series and so this one is the Taylor series part. That's the Taylor series where these coefficients are, are normal calculated derivatives and apply them. Or I could write it, if this function is periodic, I could write it as a Fourier series.
You just said if the function's periodic, you can write it as a Fourier. Is it not? You can write any function as Fourier series just with like an infinite periodicity.
Yeah, you can write any bounded function as a Fourier integral, but to write it as a Fourier series, it needs to be bounded. So it can't go off to infinity. Like, remember we talked a little about the distance between neighboring frequencies, and the neighboring frequencies, like this guy versus this guy, on an arbitrary length interval, the longer the integral gets, the closer the neighbors get in frequency. And so if you go to infinity, the sum becomes an integral because they become infinitesimally close. So, but writing it as a series like this, rather than as an integral, I should point out that this has to be a periodic function over some. Actually, here it's periodic from 0 to 2 pi, because I'm using integers as the frequencies. Okay? So this is a specialized case, but even so, we can write both of those. So these look really similar. Right? This one has an x minus a, this one has an x minus a. This one has an x minus a squared, this one has a 2x minus a. This has a series, an infinite set of coefficients. This one has an infinite set of coefficients. So the question is like, what's the relationship between the coefficients, essentially? Because there's something simple. So what about the constant part? The part at x equals a. What do I get if I plug in for x equals a in the first one? Right. So at x equals a, I have f of a equals c0. What do I have in this one? It's all of them, right? So whether you think that's a simple, I asked, is there a simple relationship? Whether you think that's a simple relationship or not doesn't matter so much. I wanted you to express them and tell me. I think it's not simple because this is an infinite sum, which is not a simple thing, whatever, to calculate what d0 would be, or what c0 would be in relation to all the d's. Okay? Does a specific term in this Fourier series relate to a specific term in the Taylor series, regardless of what function they are? Oh, and there's a hint. So I should write out the hint. hint is kind of telling you the answer to that question. Why? Why does that hint tell you? I take just one of these. Suppose I happen to have a function where only one of them is non-zero. What's the Taylor series expansion of that? It's given by the hint. The hint is the Taylor series expansion for one e to the something ix minus a. So whichever one it is, it actually has a complicated Taylor series expansion over all of them. Now, give me a Taylor series that depends on 1,000 terms. I have to sum all 1,000 of them up and pick out the different powers to sort them into the Taylor series. So it's not cleanly related. Again, it's a little bit more complicated than you might expect. This is actually the simplest case of this expansion where n equals 0, right? If n equals 0 here, then all of the Taylor series terms drop off, but n equals 0 here gives you a whole mass of ones. What about the, okay. Assuming both series converge, is there a unique, though perhaps complicated, relationship among all of the Cn and all of the Dn? So what does it mean if the Cn converges? I mean, if the Taylor series converges, what can I say about the Cn? They approach 0, and I know what they all are. There's only one Taylor series that's unique that gives you the answer every time. So I actually know all the Cn if I know the function. And if the Fourier series converges, what do I know about the Dn? They eventually go to 0, and I also have a unique version of all of them. So there is a complicated relationship. This is the complicated relationship. Figure out this one, figure out that one, and map them all to each other. It's not any simpler than that, but there it is. So, but there is a single relationship between them because both the Taylor series and the Fourier series will be the same however you estimate them, right? So 3.4, specifically, if all the d's are 0 except for d1, which is 1, so if f of x equals e to the I x minus a, what are all of the dn and Cn? Well, what are all the Dn, if that's true? All of them are 0 except this guy, right? And we know that why? Because the Fourier terms are all orthogonal to each other. So if we did that integral where we evaluate each of them, this guy will be 0 multiplied by all its product with those, its product with a constant, except for the special one, that's this one, the one that matches. So all the rest of them will go away. Okay, so if you go back to the way we derived we show how to calculate all of the Dn for the Fourier. This would tell us that only D1 survives, all the rest have to go away. Okay, so this equals 1. If n equals 1, 0 other times. What about the Cn? Here we go back to the hint. What does the hint tell us? C0 would be 1. C1 would be I. C2 would be I squared. Or in general, oops, I squared over 2. Or in general, Cn would be I to the m power over m factorial. Which you could get either by staring at this formula and remembering that the 2 here is coming from the factorial, from the Taylor series, or you could actually take the Taylor series of that function and figure it out. Both of them would give you this with a little bit of fussing. Does that make sense? And I would have been fine even if you didn't give me this formula, just to say all of them have to be non-zero, and the first few look like this. That probably would have been full credit anyway. This is an extra piece, but all of them are non-zero, and it comes from here. Cool. So, let's see, is there any other special? The one other thing that I mentioned is sometimes talking about how many roots you have in polynomials of different order, or how wiggly Fourier series are. Those concepts of like why we write the Fourier and Taylor series this way is because this one, if we truncate this, we know how many roots it could have. We know a lot about how wiggly that function is. We know about its behavior at large x, its behavior near x equals a. So that's why we do the Taylor series, is to figure that out. And we do the Fourier series because it's easy to differentiate, easy to integrate, and we know when we truncate it, we know how wiggly we've allowed it to be. We've thrown away the more wiggly bits and kept the less wiggly bits. So thinking about what the truncated forms of Taylor and Fourier mean is probably the last ingredient. That's what the midterm will have, drawing from those concepts. Yeah.
And stuff on like eigenvectors, eigenvalues, if you know if that would be stressed.
Probably not too much. I find it hard to do matrix ones that are easy enough to do kind of quickly, and we haven't talked enough about eigenvectors to really have you have a good intuition for it. We're going to do more of that. That is frequently ends up on the final, but it doesn't. I don't expect it to be on the midterm, at least in a heavy-duty way. If you kind of know what the idea is, that'll be enough. I'm not going to ask you to calculate eigenvectors or eigenvalues because it's a lot of algebra and it's not actually that helpful. The eigenvector eigenvalue stuff will be much more powerful once we've used it in the differential equations form. And so then we'll have many more of that kind of question in the final, but not so much now. I just wanted to introduce them in the matrix form. We'll spend a lot more time going through those before I feel like you guys are ready to be kind of grilled. Yeah.
What about sequences in series? Like, would we have to calculate those?
Probably not, except I definitely ask a few questions just to see if you are thinking about convergence and truncation and accuracy. I could imagine putting a geometric series on versus a power series or something like that and asking you to think about them or that kind of thing. But normally they're built into another problem when we're thinking about Taylor or Fourier being the driving motor